Hey, what is up, everybody? Today is March 19th, 2025. Today is another solid day to do Leetcode. I'm going to go ahead and practice our typing speed and see where we're at. Let's do this. Not bad, not bad. Okay. 3108. Oof, it's a hard. Minimum cost walk in a weighted graph. There is an undirected weighted graph with n vertices labeled from 0 to n minus 1. You are given the integer and an array edges where edges I equals u v w indicates that there is an edge between vectors u v and a weight of w. A walk on a graph is a sequence of vertices and edges. The walk starts and ends with a vertex, and each edge connects the vertex that comes before it, and the vertex comes after it. It's important to note that a walk may visit the same edge or vertex more than once. The cost of a walk starting at node U and ending at node V is defined as a bitwise AND. One second, I gotta take this jacket off real quick. The cost of a walk starting at node U and ending at node V is defined as the bitwise and the weights of the edges traversed during the walk. In other words, the sequence of edge weights encountered during the walk. Then the cost is calculated as bitwise anding all the weights. You are given a 2D array query where query I is S to T. For each query, you need to find the minimum cost of the walk starting at Si and ending at vertex T if their existence is -1. Return the array answer where answer I denotes the minimum cost of a walk for query I. So this is 0 to 3. Ugh. Then so okay. First we need an adjacency list. So there's n vectors. Oh my eyes. Oh man. It's an unordered or it's a undirected map, right? Undirected. Um Okay, so we have this. So the adjacency list. Oh wait, how would we handle the weights if we did that? Should be a vector-vector pair? I think so. I did this wrong. STW. I could do that, right? Um, okay. I mean, this is backwards, isn't it? It's vector of 3. Okay. Guess you can't decompose 3 characters, right? Oh, okay. Well, whatever. And let's just do this. Adjacency list E0 back E1 E2. Hmm. Okay. Okay, so we have the adjacency list. We need the node that we're on. And we're already pulling in seam. I'm too tired to do this one. So we want to go 0 to 3. This is a weight of 7, and this is a weight of 7. Oh, wow. Okay. I understand bitwise manipulation, but I'm not sure how union find fits in here. Do we just union everything or bitwise everything? If I bitwise everything in a connected graph, you're always going to get the smallest number, like 1. See, if I query 1 to 2, 1 to 2, then 1, 0. Oh, because there's probably a path. Because you could go backwards, doesn't matter. One is odd, 6 is even, which would make 0. For each query, we're just looking for the strongest connected component that it's a part of and giving it the smallest bitwise and among the connected components. Okay, so how do we do that? If it's connected, I don't even think I need to do that, right? If I just go through all nodes, and that's why we do union find, because union find will say if it's connected. If they're both connected, it's the and of all values. Alrighty Yeah, because no matter what, you and a new value, it's going to become smaller, not larger. I see. And that's why we DFS. So we want to DFS and find target. But as long as it's connected here, it doesn't matter. Okay, so how do we bitwise them all? I could just BFS, right? So let's say instead if I did this, that won't work either. DFS is to return them all. Yeah, so we would need a way of connecting the components. DFS, it's all over that one. If found, continue. Basically, we just want to say check them all. Everything in here. So we can just say if ranks I does not equal -1, continue. All right. DFS. We have my adjacency list, so we don't need to pass that in. And we're just going to be using this to mark ranks, which is there, right? And we're just going to say this is the starting node. Auto and DFS. Node and rank. Right. Then we would do rank plus plus. Okay, so we're gonna go basically we go through the adjacency list, right? I also feel like I'm going to need a scene vector. Or no, if it's already marked, I don't need to go again. So if Okay. This establishes their rank for connected components. Make sure that works. Okay. DFS. Use of undeclared identifier DFS. Oh. This needs to go above it. Oh. DFS. There you go. No matching function call for call type lambda DFS. DFS child rank. Child has a weight. This is a pair. Zeros and one. Okay. And zeros. Those are all strongly connected. Okay. Okay, this gives me the ranks per node. Now, if the ranks are the same for the query, then it's everything for that node edge, right? For rank whatever, which I have here. Actually, let's do this. So this gets my ranks. Now we're going to do should I do the no. Let's say 0. Yeah, per rank. So it's we want a map and it's going to be rank to bitwise, right? So we get a rank 0. So this tells me how many ranks there are. Okay, this gives me a max rank, right? No, we don't even need to do this. Hold on. We can do this. Okay. So rank I is not equal to -1. We'll continue. Which means rank I is -1. We make it 0. We assign 0. Okay, so this is rank 0. Then rank 1, blah, blah. So this rank is max rank at the end. Okay. So then we want to go 0 to rank. It's going to be equal to, because it's 0 indexed. And then we want to map, we want to breadth first search the node. Wait, but how do we know what rank 0 node is? No, that's not going to work. Oh, less than in. It will say if the rank to bitwise is found. Rank to bitwise dot find. I does not equal rank to bitwise dot end. Continue. Okay, so if this is the node, we don't want the node, we want the rank. So we're gonna go rank. Okay. Then we're gonna go int bitwise. No. What we want to do is we want to go q pair int q. No, how are we gonna do this? Give me a second. I'll be right back. First off, um, okay. Okay, I'm back. So we need a value that is all ones. Let's see. Can I just use int max? Would that work? I'm gonna try it. I want to see what happens. So let's go ahead and q.push 0 and while not q.empty, does level order matter? I don't think so. Q's auto u equal auto node weight front up. I might need scene here. Oh wait, child is the node. This is where it's going to the next one. And then for every node that we have in here, right? And then this I want to do in here. Well, first off, this is I. Okay, this gets the bitwise and from here. And then we can say rank to bitwise of I equals bitwise. And then when we have a query, say node 1 and 2, or in this case 0 to 3, 0 to 3, if the query, or if the ranks are equal, then it's the minimum. Or no, if they're both equal, then rank to bitwise should just be whatever this rank is for this node. Yeah, so we're just going to go through query. Actually, let's do this instead real quick. Because I'm not going to have that many ranks, right? So this is ranked to bitwise, not node. So we established ranks here. So we're going to go ranks I equals the bitwise. Invalid operand to binary. Oh, is it because it's a map? I'm not looking for the key. They're both 0. We set it to int max. Oh, wait. From this node, we said 0. That's not going to be right. We actually need to do this. So not wait, but child.second. Int max and 1. So wait, hold on. One is right. This is never set. Wait, so if we start at node 0, node 0, standard out. Hold on. Cout r dot first. That 0 to 3 is 1. 3 to 4 don't match. Okay, 0 to 1. Oh, rank 0. Yep, rank 1 is set to -1. Let's see. They're all connected. 7. Oh, wait, hold on. Bitwise and equals this. Child.second. Actually, it might actually be better to do this anyway. Even if it sees it. Because that will be 0. But it'll still update, right? And then if I did something like We need a vector int. If rank 0 rank, I'm sorry, if ranks if ranks blah blah blah. Okay, we can just say result. Zero. If the ranks are the same, I'm not sure if this is gonna work though. I mean, it works for this example, but I got pretty far. Zero. But it's set to int max. Hold on. If bitwise max did I do that? One to zero. That might break it, maybe. Edges. There's 6 nodes. There's one edge, 4 to 0, or 403, or with a weight of 3. We want to query 40. Hold on. Query I0. I said 4. Equals. I gave him the query, not the rank. Yeah. Oh, man. Okay. Memory limit exceeded. Is it because I'm doing it by rank? Doing them all. How big is the thing? Weight of 1. And I'm using an unordered map to do this. Okay. What if I did, instead of this, I went vector int, a single vector int, and then this is going to be rank to bitwise. I will set them all to int max. Or no. We don't really need to find at this point. What we need to do is say if rank to the overhead on unordered map might be what's messing it up. Oof. N is 100,000. I don't think... Hold on. There are going to be 100,000 nodes. Actually, yeah, you can just label that as in. Memory limit exceeded. Adjacency list, rank to bitwise, ranks. Well, this is sad. Let me think. I don't use like using bool, but it will make it. Oh, I mean, my memory is still terrible, but converting scene. Oh, because I'm using int over and over and over again. Bool would be way better. Okay, that was probably not the best solution, but we will hopefully on our own time look up the solutions that might be better for memory. Anyway, woo! I solved a hard. How long did that take? Close to an hour. Okay. Well, thank you for joining in. This was a nice problem. I'm glad that we got to solve it. Next time, I probably should have just used Union Find. Okay. Have a wonderful evening, everybody. Later. Peace.